structure and nomenclature of organic compounds. So structure we've haven't really discussed on the board. Nomenclature we've briefly mentioned. Nomenclature is a fancy way of saying naming of, right? Naming of organic compounds. Organic simply refers to carbon. So if we refer to organic chemistry is carbon chemistry. So inorganic chemistry is non-carbon chemistry. So all of your ionic salts, etc., that's all inorganic chem. All right, key knowledge straight from our study design. Carbon atom reference to valence number. What is the valence number of carbon chemistry, of carbon? What's the valency of carbon? 4, excellent. Bond strength, stability of carbon bonds with other elements in the formation of isomers. So why is carbon special? It's often a question I ask year 11s. Why is carbon special? Right, can form 4 bonds, and so it can form them in single, double, triple bonds. So it can form almost an infinite variety of different bonds, particularly with hydrogen, right? And different lengths and different shapes and so on. It is it's the basis of life is carbon-based chemistry. Formation of isomers, structural, right? So we have looked at some structural, so branched and positional isomers would be referred to as structural isomers. We've got this other thing called stereoisomers, which is new, wouldn't have been talked about last year. To explain carbon compound diversity, including identification of chiral centers, another new term to you in optical isomers, of simple organic compounds, and the distinction between cis and trans isomers. Again, that is something new to this year. You may have just covered it last year or as an extension last year. So geometric and stereoisomers are new this year. There's also a number of new functional groups in which we'll explore as well. Structural, including molecular, structural, and semi-structural and skeletal forms. So we've seen structural and semi-structural before. Skeletal we haven't, but it's not that much different, and I'll show you that either today or next lesson. Alkanes, including cyclohexane. So it's there are only 2 cyclical compounds you need to know. One is cyclohexane, the other is benzene. We don't look at any other cyclical compounds, okay? Otherwise, we're adding too much complexity to the course, and there's enough in organics already. Alkenes, seen that, right? Alkynes, benzene, right? Haloalkanes, another functional group. So haloalkanes, we add a halogen. Primary amines, something new. Primary amides, something else new. Alcohols, both primary, secondary, and tertiary, the distinction between them. Aldehydes, ketones, carboxylic acids, and non-branched esters, right? So they make that really clear. Only linear-based esters present. IUPAC system naming of organic compounds up to C8, up to octane, no more than 2 functional groups, where a branch is considered a functional group. It's not really a functional group, but a branch does change the physical properties of a substance. Alcohols, carboxylic acids, and non-branched esters, right? So we don't need to know how to name amides, aldehydes, and ketones, okay? So only primary amines. We'll talk about what we mean by primary, secondary, and tertiary. So I've seen this before. Much of it is on the board. Carbon, I asked why it's special. It's got a valence number of 4. Single carbon-carbon bonds, saturated double, carbon-to-carbon double bonds, or triple carbon-to-carbon triple bonds, both unsaturated. Homologous series of alkanes, alkenes, and alkynes from last year. Homologous meaning the same, similar structure, a pattern to their physical properties. Right? What is that pattern? As we increase the length of the hydrocarbon chain, what do we expect in terms of their boiling point? Increases. Yeah, exactly right. if we add a functional group, what do we expect will happen with the boiling point? It will, well, you've got choice. Increase, decrease, or no change. If I add a functional group, what effect? It will increase. Why? What's common between particularly these functional groups? They are what? You mentioned it before. What did you say? Didn't write on the board. We talked about, starting with P, polarity. Right, so the more polar a functional group, it has a greater effect on the boiling point. Right, the more polar the functional group, higher the boiling point, higher the solubility. Yep, so those two things, the more polar the functional group and the longer the hydrocarbon chain increases the boiling point. Similar chemical properties, right? Chemical properties, really we're talking about things like bonding, we're talking about their flammability and so on. General formula, each subsequent member differs by a CH2 for any given series. Alkanes, seen that, nothing new, all on the board. Entirely hydrocarbons made up of carbon, hydrogen, CnH2n plus 2, they're saturated. It's important, talking about saturation, that's important when we get to the next part of the topic in the chapter 11 related content, because bonding of alkanes is, not bonding, what was I talking about? The reactions of alkanes is different to the reactions of alkenes. All right, some old and some new things here. So we've seen this before. Molecular, structure, and semi-structure, or also called condensed. Molecular tells us the type and the number of atoms within the molecule. So just looking at those first three. Methane CH4 has a structure, right? C, 4 single bonds coming off it, not expecting, right, those three-dimensional representations where you got the zigzag lines, etc. Right? BCAR is very happy for your molecules to appear flat. Semi-structural, right? Semi-structural essentially removes the bonds and collapses it to grouping around individual carbons, right? So we've got CH4, or ethane goes to CH3, CH3, propane goes to CH3, CH2, CH3, and so on. Condensed is slightly different in that we would, if we go to say butane, we would then group CH2s together. So butane would be CH3, CH2 in brackets with a 2, and then CH3 at the end. Skeletal's a bit different, right? May not have seen this before. It's a shorthand version of molecular formula. It shows some of the geometry, not the individual atoms present, unless there's a functional group. So if there's a functional group present, we show the functional group. So it's useful for really large molecules, right? And the point at which is the number of hydrogens present is implied. So if we look at butane here, let's get a laser pointer to make it more clear. Look at butane, right? I can see that this vertex, right? I've got 2 bonds coming off that vertex. We know that carbon atom wants to have 4 bonds, so it's implied that this is CH2, right? This terminal carbons here, right, at the terminating points, only has 1 bond. Carbon wants 4, so it's implied that it's a CH3 on the end, right? So if we see a point like that, we know it's a CH2 at the vertex. If it's only 1 bond coming off there, then we know that's a CH3. If I had a branch group coming off here, that would be 3 bonds around that carbon and therefore only 1 hydrogen present. Yeah? Make sense? Okay. So that's important, particularly when we look at chiral carbons and the identification of chiral centers, which I'll talk about later. Something new, cyclohexane. Cyclo referring to a ring, right? Hex meaning 6, ane referring to all single carbon-to-carbon bonds. The difference is that in cyclohexane, we refer to it has the same molecular formula as hexene. So cyclohexane has 1 degree of unsaturation, because in order to close the loop, notice here, we will lose 2 hydrogens. So see how these terminal ends are CH3. We lose 1 of those hydrogens on each of those in order to complete the loop. So it has the formula C6H12. Hexane, normal hexane, C6H14. Cool? We have something to just flag for later. Around single bonds, we have rotation, right? So if we think about this chain of the molecule, we can rotate that in such a coordination that we start to look into a ring, and then we lose those 2 hydrogens as we bind those 2 carbons together to form a ring. So here would be our kind of semi-structural formula, even though the bonds are appearing, and this is our line formula. Are there any questions about cyclohexane? We can have other cyclical compounds not really explored this year. So you can have right down to cyclopropane. The difference is cyclopropane is really unstable because the bond angle is very small, and so there's a huge amount of strain in that molecule, and it breaks apart very readily. Same thing with cyclobutane, whereas once we get to cyclohexane, the bond angle is, can't remember, what's the interior bond of a regular hexagon? What would it be? 360, 729. Brain's not working today. Anyway, so the bond angle is such that it's much more stable. Naming of alkanes, we've seen that on the board, right? We've got some naming rules. Up to oct, so meth, eth, prop, but, pent, hex, hept, oct. Number 1, find the longest continuous carbon chain. Second, identify and name the functional group. Name the chain consecutively starting at the end nearest to the highest priority functional group. I'll talk about the priorities later. Number 1 priority is carboxyl, followed by hydroxyl. And then there's a few others in between. And we end with haloalkanes as the lowest of the priorities. We designate the location of each group by the appropriate number and name. So but1-ene would be 4 but, a double bond coming off the first carbon, for example. Listing groups in alphabetical order. So if I have both a methyl group and a chloro coming off the carbon, the chloro would be listed first, followed by the methyl. I'm not going to be as picky as to whether you list it in alphabetical order. That's just standard notation. The picky bit is more that you are designating its location correctly. Branched alkanes, right? Remember, we are naming or numbering from the end closest to the branch or closest to the highest order functional group. So I want you to think it's not left to right, it's nearest to the end appropriate. So in this example, we've got the methyl group here. So it's not 4-methylpentane, right? Because if I take that molecule, rotate it 180 degrees in space, I get exactly the same thing. So that's why I number from the end closest to the branch, we get 2-methyl. Methyl group, single carbon, 1, 2, 3, 4, 5 carbons in the longest chain. So it's pent, all single bonds, ane, methyl group, so methyl, pentane, 2 coming off the second carbon, 2-methylpentane. And then where I've got butane. Now, butane's an interesting case. We've got butane here, and this is just methylpropane. Why might it not be 2-methylpropane? Anyone want to have a guess as to why that would not be called 2-methylpropane? Yeah?